so from the equation, you'll notice that I have the equation in this form, A sine BX plus C, okay? A, B, and C are all just numbers here that could possibly be given to you. So if we have the equation, we could type it into Desmos, we could look at the graph, and we could find those things. But honestly, it's easier to find it from the equation if you just know the standard form for this. So whenever you have this equation, and notice it's exactly the same except for one of them has sine, one of them has cosine. So it does not matter whether they give you sine or cosine. The answers to these will be the same. The midline will always be y equals c. Okay, and if you think about it, that number added onto the end of the graph moves the graph up or down. We talked about moving graphs with transformations earlier. And that'll move the graph up or down, and if you move that graph up or down, the midline moves with it, right? So y equals c is going to be your midline. Your amplitude is the absolute value of A. So amplitude is just the number out front, but it is the absolute value. Amplitude should always be positive. So if you get a negative out there, the negative... What does a negative do when we put a negative in front of a graph? What? I mean, yes, but it flips it upside down, right? So the negative and the amplitude are separate right there. So amplitude is always positive. If there's a negative out there, that negative is flipping the graph, not making the amplitude negative. Does that make sense? So this should always be positive, but it's just this number right here. The period is the trickiest, but it's not terribly tricky. Normally, if you don't have any transformations to the period of your graph, it would be either 360 degrees if you're in degrees, or it would be 2 pi if you're in radians. Because on that unit circle, that's how far it takes to get all the way around the circle. And then after that, you just keep repeating, right? So, so if we have a number on the inside right here, this B, the way that we find the period is if we're in degrees, we'll do 360 divided by B. If we're in radians, which is what you're more likely to see, we'll do 2 pi divided by B. Okay, questions? All right, let's look at this when we're actually using it. Okay, and I am gonna split screen mine so I can graph this for us here too, because you can always look at the graph if you would like for this. You don't have to do it just from the equation. I will say that in general, we probably want this to be in radian mode right here. So if you are following along on your computer, yours is probably degrees. You might want to flip it to radians. So the midline is always y equals that last number right there, that -1. So y equals -1. You can check it by typing it into Desmos, y equals -1, and making sure that is in fact the line that cuts through the middle of the graph, and it is here, so that works well. Okay, let's see, the amplitude for this is just the number out here. It's the absolute value of that number, so if that number is negative, you would make it positive, but this one's positive anyway, so my amplitude is just 4. And if you look over here on this graph right here, you can see the distance from that midline up to the highest point is 1, 2, 3, 4 units there. Okay? The period of the function is going to be the amount of time that it takes for the function to start repeating itself. So if we are using the formula from the equation, we're going to look at this number right here, but that's not our answer. We have to do, if we're in degrees, we do 360 divided by 3, which will give us 120 degrees. If we are in radians, we'll do 2 pi divided by 3, which won't reduce, so we'll just leave it 2 pi over 3. Now, on your graph right here, if we're trying to see, where the period is on the graph, I always like to start right there at your y-intercept, where x equals 0. And you're thinking about how far you have to trace this graph before it starts to repeat itself. Right here, if I took like that part that I have highlighted and made like a stamp, I could just stamp it over and over again and get this graph, right? So it's from here, which is at 0, over here, and if we click right there, that is, in fact, at 2 pi divided by 3 for that. So from the graph, that's what you do. From the equation, you just have to do 2 pi divided by whatever number's in front of your x. Okay, questions? All right, so let's do one more together. Our midline is always y equals this last number right here, which is -40. The amplitude is the number out front. We do have a problem here. Do we have a number out front? We do not. What number is there? 1. Our amplitude is 1. You always have an amplitude. If there's no number out there, then it is a 1. Don't put 0 and don't put none. There's always an amplitude. If there's nothing there, it's a 1, because we would have like an invisible 1 out front. Okay? Now, this middle part is tricky. Theta right here is your variable. That's like your x. So, whenever I see this right here, this is the same as having 1/3 times theta. So the number out front is 1/3, not 3. Because this is theta divided by 3. Do you guys see the difference between this on number 3 and this where we're dividing right here? If it bothers you that that's a theta, just turn it into an x. That's your variable. But they might use a theta on the exam, so I wanted to throw that in here in case they do. It's your variable there. Actually, there is a mistake on this right here. That should have been f of theta right there if it was going to be theta right here. Or if they both need to be x. One of the way. All right, so to do this, we have to divide. We'll do 360 divided by 1/3. And 360 divided by 1/3 is going to be 1080. Or if we're in radians, 2 pi divided by 1/3 is going to be 6 pi. Because dividing fractions is easy as pi. Like when we do 2 pi divided by 1/3, dividing fractions is easy as pi. Flip the second and multiply, which will just give us 6 pi. Perhaps, though, we want to just look from the graph. So if I've got y equals sine of x over 3 minus 40, I'm going to get rid of this old stuff. I'm going to get rid of that highlight right there. I don't even see the graph. Why do I not see the graph? -40. So I need to, I really don't need to zoom out as much as I need to like scroll down a little bit, right? So right there is my graph. And if I want to check the midline, type in y equals -40. See if it goes through the middle of the graph. It does, so that looks good. The distance from the midline up to that highest point is just 1, right? So my amplitude is 1. The period, to me, is the most difficult to find on the graph, but you're just going to start right there at the y-axis, highlight until you start to repeat yourself. And if I look over here at that place where I start to repeat, it is 6 pi for that. Okay, questions? All right, try 5 and 6 on your own. You don't have to bear, just put an X. That theta, you have to type in as an X right there. So right behind, it's got to be in the X, right behind that pi. Good. Yeah, and then put your, now, yours is crazy right now. Hit the house button. Out. And then, hit your wrench. Okay. It's zoom out a little bit. One thing you could do to get research over here, the y-axis is really all we need to like trim down. So make that like maybe something right there. Right there. Double click the class, see it'll like highlight all. can kind of see like the midline. Right. So that's also be white. Yeah, because it's the number added on the film, but it's not, there is no number there. So it's white. If you type in y equals 0, it'll be like straight to the middle of it, right? And then the amplitude is 10, that's perfect. That's this number, and you're just going to use 1 on. That's great. The period, if you look right here, start at 0, right? So we go up, then we go down. That point right there is our period in the graph, which is 1.6. So that would be your period graph. That's in radians. You can change it to degrees and see. All right, let's look and see what we got. All right. Oh, I messed that up. Okay. All right, so midline for number 5 is y equals 0. There is no number added to the end, so you could put a plus 0 right there, and that would be your midline. See, Maya, what's the amplitude? It's 10. Okay. For your period, if you're in degrees, which this is probably not in degrees actually, because it has a pi in it, but it could be. It'd be 360 divided by 5 pi over 4, and it's okay with me if you guys just get a decimal for that. If it probably gives you a decimal. What did you guys get? 91.67. All right, let's see. I'm going to double check. Yeah, that's what I got too. There. Probably you won't see that. What you'll probably see is in radians where it's 2 pi divided by pi, 5 pi over 4. And I'm going to do this up here because I don't have room down there. So I've got 2 pi divided by 5 pi over 4, which means I need to flip and multiply. And I'll just multiply straight across, so I will get 8 pi over 5 pi. The pi's cancel, and I just get 8/5, which is 1.6. So you can either give the fraction or the decimal. It does not matter there. Okay. For number 6, Riley, what's the midline for number 6? Y equals 3. Okay. Scarlett, what is the amplitude for number 6? Almost. What should it be? Positive. It's always positive. So if there is a negative there, it flips the graph. It does not make the amplitude negative. Amplitude should always, always, always be positive for that. And then for our period, do we have any number multiplied in here? We got nothing. So that means it's just a 1 there. So you're doing, technically you're doing 360 divided by 1, but that is just 360. And over here, technically you're doing 2 pi divided by 1, but of course that would just be 2 pi. Okay, questions? All right, so these problems can be used in a lot of different application sort of problems. So one of the things that acts according to like a sine function, or pretty close to it, is the hours of daylight. So we are getting really close to the shortest day of the year, right? I think it's December 21st is your shortest day of the year. You got the least amount of daylight. And then after that, our days will start to get a little bit longer again, right? So whenever you, like if you were to graph that, your lowest number of hours of daylight is going to be December 21st. Then it's going to get more and more daylight until you get to the summer solstice, where you have the most daylight, and then it goes back down, and every year it just keeps on doing that over and over. So this function right here gives the number of hours of daylight in months after the summer solstice. So the first thing it says is what's the period of this function. So you now have two different ways that you can look at this. So if we just use the straight formula that we just learned, we would look at this number right here. And let's do this in radians. Most of the time they ask you these questions in radians. We would have to do 2 pi divided by 2 pi over 12. And dividing fractions is easy as pi. Flip the second and multiply. And we want to make this first pi 2 pi over 1, since it was not a fraction. And the nice thing that happens here is the 2 pi's cancel. So you just get 12. Does that make sense for this situation? How long does it take for your daylight patterns to start to repeat? 12 months, right? It's 12 months. Every 12 months, every year, it starts back over, right? So like we're about to be to our shortest day of the year. Then we'll have a whole year, and next year on December 21st, we'll be back to our shortest day. And then it just keeps repeating over and over and over again. So 12 months would be our period. Now, if we look at it on the graph, we've got, I'm going to use y equals 2 cosine of 2 pi over 12 times x plus 12. And I can't see it right now, but that's just because I need to zoom in a little bit. And we can see here, if I'm looking for the period of the graph, I'm looking for how long it takes it to repeat. So for this one, it starts at a maximum point there. So once I get back up to that maximum point again, it's going to start to repeat, right? So if I look at that, if you click on it, it'll give you all your maximum minimum points. And right there, the x coordinate of that is 12. So from 0 to 12, that's your period. Okay, questions? All right, maximum hours of daylight this town sees in a day. There are two ways you can do this. Our midline would be our line in the middle, right? Our amplitude, what's our amplitude for this function? 2. So the line in the middle plus 2 would give us our maximum, right? So I could just do 12, which is our midline, plus 2, which will be 14 hours. Or probably the easier way on this is to just graph your equation, click on it, there you got your maximum. It doesn't matter which maximum you click on, all of them have a y coordinate of 14, right? What's the minimum going to be without me clicking on one of those? 10, right? Because it would just be 12 minus 2, which would give you 10 hours. But, of course, you can click on that lowest point, you'll get 10. What's the average amount of daylight that the town sees? It is 12. This is that midline. Okay, now this changes where you're at. It actually, if you look at the actual data, it also becomes less sinusoidal. It's like a little more like zigzaggy, but we could still use it to approximate. But if you are in Alaska, what's going to happen? What happens in Alaska? Like if you live in... Right. So what happens like up in Alaska is like the amplitude changes and is a lot bigger, right? Because depending on where you're at in Alaska, especially if you're like way north Alaska, you have some days that the sun does not set, right? And then if you're like maybe further south in Alaska, you might not get that, but you might have like only 1 hour of daylight or 1 hour of nighttime, depending on where you're at. So the amplitude gets really big on that because it goes, way above, way below on that. This summer we went to Germany, which I did not realize this was going to be like something that I experienced while I was over there. Germany is a lot further north than the U.S., or definitely than North Carolina. It's a lot further north. The jet stream keeps it warmer, so the climate's very similar, but it's a lot further north. So we were there in summer, in June. It was really close to the summer solstice, which would be your longest day of the year, and it was daylight at 4:15 in the morning, and it stayed daylight till 10 o'clock, 10 p.m. So we were far enough north that there was a big difference in your daylight hours versus what you would normally see at home. Because here it would be after 5 before it would be daylight, even on that longest day, and then it would get dark at 9, right? So it was noticeable. It was kind of neat. So let's continue on. This is one of my favorite problems. Right here. I find this fascinating. A few years ago, I read a book that was called The Devil in the White City, and it's written by Erik Larson. I don't know if y'all have had to read Isaac Storm for anything. Sometimes they assign that one in school. It's a really, really good book, too. But the book is a really interesting book that's about the Chicago World Fair in 1893. And the book kind of goes back and forth between two storylines. One of them is about them preparing for the World Fair and everything. The other one is about a serial killer that operated during the World Fair in 1893. The World Fair in 1893 was sort of a disaster. It did not go as well as they were wanting it to go. And there was a serial killer that operated in there. He had a crematorium built in this apartment complex that he used, and he would kill people and then burn them, and that it was bad. Anyway, very interesting book. It's a little dark, but very interesting if you ever want to learn about. But what I found very interesting from a mathematical standpoint is the Ferris wheel. We've all seen a Ferris wheel 1,000 times, right? Probably ridden on several Ferris wheels. It is called the Ferris wheel after the man who built the very first Ferris wheel. The very first Ferris wheel was built for the World Fair in Chicago in 1893. 4 years before that, Paris had hosted the World Fair, and each World Fair, each city tried to do something big that was unique for their city. Does anybody know what was built in Paris for their World Fair 4 years before this? It was the Eiffel Tower. That was built for the World Fair. It was a big showpiece for the World Fair. So the U.S. was hosting it 4 years later, and they needed to come up with something big and new that, but they didn't want to do a tower because that would just be kind of copying the idea. So we had never built a Ferris wheel before. Never. Ever. Nobody had ever ridden on a Ferris wheel. So they decided to build a Ferris wheel that had a diameter of 250 feet. At 250 feet, is probably a 20-story building, right? And at this time, this was about the height of the tallest buildings they even had. We didn't have skyscrapers in 1893. People did not build things this big. So we decided the first one that we were going to build would be 250 people. Each one of these cars right here holds 60 people at a time. So 60 people each are in this car. That means, and there's 36 cars, so there was 2,160 people that you could fit on this Ferris wheel. At one, we'd never built one before. We weren't sure it was going to work. We didn't know if all those wires were going to hold and it might just fall apart whenever they started. The tallest building at the time was only 348 feet tall. So this is almost as tall as like the highest skyscraper that we had. It was powered by a 1,000 horsepower steam engine. It cost $400,000 to build. They charged you 50 cents for a 20-minute ride. It takes 9 minutes for the thing to go all the way around if it's not stopping right here. So this Ferris wheel here was the very first one we ever built. In the book, it talks about like the first time they ever like turned it on. It was like they didn't even have the cars on it yet, and they weren't sure if it was going to work. And the first time they ever like powered it up and turned it on, it talked about all the workers that had been on the Ferris wheel just like grabbed on to all those like steel rails right there because there were no cars on it yet and just rode it around. Just like, just grabbed on and rode 250 feet in the air because we were obviously a little less safety oriented back then. Another interesting story, it was like these cars right here had glass all around them. They were totally enclosed. And they had a door, but the door did not lock. Because, it was, 1893, and we were not nearly as concerned about safety. And which was, like, you still weren't going to fall out. It was okay, except for it tells a story about one man that got on the Ferris wheel and got up towards the top and completely, like, went crazy because he was so scared of being, like, people did not go this high. Like, they might climb a tree is about, the highest they went. They didn't even go, most people didn't even go in buildings this high. So, got to the top and, like, went crazy, and he was, like, trying to, like, get out of the door, and it didn't lock, and so they had to, like, tackle him and hold him down. The other 59 people in the car had to, like, attack this man and subdue him so they got back down to the ground. So, anyway, I find this very interesting. We can use a sine function to model what's happening here. So, if we want to write a trig equation that will model the height of a rider X minutes after entering the first Ferris wheel, okay? So there's a few things we need to know. We need to know amplitude, we need to know midline, and we need to know what the period of the function would be. So for this, right here is the center, right? And that is 140 feet off of the ground. So that is my midline, right? The center of that Ferris wheel is my midline. So midline equals 140. But this Ferris wheel does not touch the ground whenever it goes around. There's like a platform you got to go up to, right? Because it'd be a little bit difficult for it to rotate if it was scrubbing the ground each time. What is the amplitude? Amplitude is going to be the same as the radius here because it, like, from, let me use a different color, from like here to here, that's from the middle to the lowest point that you go, or from here up to here is from the middle to the highest point that you go. So your amplitude is half of your diameter, so your amplitude would be 125. Okay? And the period is how long it takes for it to start to repeat, right? How long is that going to be for this problem? You can't really tell from the picture, but there's information over here. It's 9 minutes. So period equals 9 minutes. That's the information that we need. So, if I go over to the next slide, fill that in. Look at the picture. So, our midline is 140, amplitude is 125, period is 9 minutes. Okay? parts of this equation are really easy to come up with. The period is a little bit more difficult. So we're going to have y equals, amplitude goes first, 125. We'll do sine of, and then right here, I'm going to, wait just a second. I'm going to put an X right there. I'm going to put a B X right there. Because I don't really know what this number right here is supposed to be. I'll tell you that it is not 9. You don't just plug that number in. You don't just plug the period in. And then my midline is 140. Right? So, for this number right here, you got a couple options. We could pull up Desmos again. We could like type in what we've got. Y equals 125 sine of bx plus 140. And I'm going to add a slider for b. And it's a little hard to see right here. Zooming out makes it bad. Like you can't tell what's going on if you zoom out. So I'm going to hit the wrench button. And I'm going to make my x's. X is your time, right? So we maybe want to know like 20 minutes of this, right? Because that would be a couple. So if I go from 0 to 20 right here. And then on the y-axis, I definitely don't care about, like I want it, 0 would be the lowest it goes. The highest is like 300 or something like that. And I can get a little bit better picture. And I'm going to type in y equals 140, which is my midline also. There's mine. Okay, there we go. There's mine. I didn't have my x-axis showing up there, or y-axis. So, right now, if I look, the period of this graph, if I go up and then down, it starts to repeat right here. Right now, my period is 2 pi, right, because I don't have a number in here. 2 pi is 6.28. That is not it. So, if I want it to be a little bit longer than that, so I would be trying, if I do x equals 9, I'm trying to get it to like repeat right here. Oh, that's really close right there, negative 0.7. Let's see. That might be it right there. Oh, wait. 20 pi over 7, what's showing up there? Okay. I bet it's going to be 20 pi over 7. So, most of the time you'll have answer choices so you can plug them in, right? So that makes this problem a little bit easier. If you don't have answer choices, what you can do is you can say 2 pi over b equals 9. Actually, it's not going to be 28 pi over. I don't know what that was. And then, so if I want to solve that, I would multiply both sides by b because I can't solve for it when it's in the bottom. So I got 2 pi equals 9b. And I divide by 9. So b equals 2 pi over 9. So that is the number that goes right here. So my equation would be y equals 125 sine 2 pi over 9 x plus 140. And if we graph that just to make sure, let's change this to 2 pi over 9 right there. And then I can see, oh, it starts to repeat perfectly at 9 right there. Okay. Again, you usually have answer choices for this, which makes that a little bit easier to do. So the height of the rider is going to just, it goes up and down, up and down, up and down, over and over and over. So in some calculus, you can talk about speed and all of those things. Okay. let's look here. A group of EHS students decided to study the sinusoidal nature of tides. Values for the depth of the water level were recorded at various times. At t equals 0 hours, low tide was recorded at a depth of 1.8. At t equals 6 hours, high tide was recorded at a depth of 3.6. Sketch the graph of this function and write the equation expressing distance in terms of time. All right, so for this, let's sketch what's happening here. Wait, let's my axis. Let's try that again. Okay, so the lowest that we go is 1.8, right? The highest that we go is 3.6. Okay, so we are at 0. We are at low tide. At 6, we're back up here at high tide. And then, so when will we be back to low tide? 12. We'll be back to low tide. And so we got this graph right here. So we need to know, really the midline's the first thing you need to know. We need to know that line that goes through the middle of that. What would it be? Or how would we find it? It's going to be halfway between 3.6 and 1.8. How do we find a number halfway between two numbers? Add them, divide by 2. So we'll do 3.6 plus 1.8, divide by 2, and we should get 2.7. That's my midline. So we're going to have y equals, I'm going to leave some space right here, sine of something x, and then we'll have plus 2.7 over here. What is my amplitude if this is at 2.7? Amplitude's from the midline to the highest point. Right? What's my midline? 2.7. What's my highest point? 3.6. So to find that amplitude, I just do 3.6 minus 2.7, which is going to give me 0.9. So that will be my amplitude. So that's why I need to find the midline first, because you got to use it to find your amplitude. And for that period, you would need 2 pi divided by b has to equal, how long does it take our graph to repeat here? It doesn't repeat at 6. That goes from low to high. You got to go from low to low to repeat, right? How long is it from low tide to low tide? 12. So that's supposed to equal 12. So we would multiply by b. 2 pi equals 12b. Divide by 12. So you get 2 pi over 12. Or it might be reduced to pi over 6. Either one is fine. There. So let's graph that on Desmos. Okay, and actually, instead of calling that y equals, I'm going to do f of x equals for a really important reason here. All right, so this is my graph. Low point is at 1.8, high point is at 3.6, midline is at 2.7. So that looks like it's pretty good. It looks like it probably starts to repeat. Let me graph y equals 2.7. It helps if the midline's there. If we look, it starts to repeat at 12, so this is accurate right here. This question says give the depth of the water at 21 hours. So once you have an equation if I want to know at 21 hours, all I have to do is plug in 21, right? So I can do f of 21, and I get 1.8. It'll be low time. All right, so we'll get 1.8. Okay, questions? Okay, so I have an activity for us to do for this, but we are so low on time. What I want to do is instead is if you go to Canvas, we've got a bunch of reviews. Okay, I believe Part D and Part E are the ones that deal with this. Let me make sure that's right. Okay, yes. Part D and Part E are the ones that deal with our trig stuff. So what I want you guys to do is I want you to start on the review, but start with Part D and Part E. Okay, and I'll be around to help. We may even stop and go over a couple of them together. If you get those done, you can work on A, B, and C. Okay? What you don't get done is going to be your homework. What I'm going to do is I'm going to look at your assignments. I don't have these going into the grade book individually because they count for too many points right now. I don't want that many points going in as one grade. So I will look tomorrow and I'm going to give you a homework grade that's worth 5 points. And you will get, like, however many of these you got done, that's how many points you get. You do have to make at least a 50 to get credit for them. Okay, it should let you retake them if you don't make at least a 50. Because I don't want you just going through and clicking things. But you do have to make at least 50 to get credit for them. All right, so